sharing behind the scenes of what I'm doing to prepare for next Friday, next week, the 3rd of October's session, where we'll be going through the F35 accident investigation report for an accident that occurred in Alaska in January this year, 2025. Excuse me, and we'll go through talking about the control structure model and how we do the analysis, and looking at it from both an STPA and a cast accident analysis perspective. Now, of course, if you've got any questions or comments, you're welcome to stick them in the chat below. As I said, there is a delay of about a minute between you typing it coming up on the screen, and then me seeing it to do something about it. So please be patient. I am recording this session. I'm going to try and put it on YouTube as well. I forgot to do that yesterday, so that was a bit of a mistake on my part. But I will make the replay available on YouTube as well. So yeah, great to see you all. Thank you for coming. And of course, remember to register for attending next Friday, the 3rd of October's webinar. Right, now let's get stuck into it. So where is it? Share, large screen. There we go. Should be able to see everything now. Should be able to see to Miro. So this is a piece of software called Miro or Miro. I don't know how to pronounce it properly. And essentially it's like an infinite whiteboard. So you can put slides on there, PDFs. You can do drawings on there, and you can also co-work. So if you have a team of people, they can all join Miro and they can all work together and do brainstorming and masterminding and analysis together. And I use it quite extensively. But in terms of yesterday, where we got up to yesterday, we started going through the official investigation report, which was published relatively recently, and we managed to get all the way up to Section 5 maintenance. So what I intend to do for the next hour or so, I will continue through this investigation report, making notes, annotating things, and of course, if you've got any questions, I'll attempt to address those as we're going through. So let's get stuck in then. So Section 5 maintenance, that's where we got up to. There we are, maintenance. So this shows a crash site overview. I think that should be big enough on your screen. Yeah, it looks like it. Fantastic. So we've got pilot recovery chute there, ejection seat, impact site, taxiway Sierra, and then of course the flight line. So there's all the aircraft over here. So, you know, that huge, what was the cost? 196 million, I think it was. There we go. $196.5 million. If things had just been slightly different, they could have had more casualties and more damage and destruction. So this was, whilst it lost an aircraft, this was a near miss. This was a real lucky situation. I think they got off quite light, and it suggests that there's some potential serious issues with the control structure, which we'll, of course, identify as we're going through this. So then maintenance then. So let's have a look at this maintenance, Section 5. So forms and documentation. The autonomous logistics, here we go. This is interesting. Autonomous logistics information system. That might be a candidate for inclusion in our control structure model. So we'll have to keep our eyes open for that and have a think about it. In fact, actually, before I get stuck right into it, would you mind typing in the chat and just let me know that you can actually hear what I'm saying and I'm not just talking to myself? Because I do get a bit paranoid that perhaps the audio's not made it through as well as the video. Fantastic, thank you. So the ALICE is a program used by F35 maintenance personnel to document servicing, inspections, aircraft configuration status, and houses joint technical data. So joint technical data. So F35 maintenance personnel, they'll certainly be in our control structure model. Used to maintain the aircraft to manufacturer specifications. No major discrepancies were noted regarding documentation of maintenance performed on the mishap aircraft. Okay, great. Inspections. The post-inspection report, post-operation inspection is completed after the F-35 completes its final flight of the day, before operations service, also AF and BF in traditional speak, before flight and after flight is required before the first flight of the day. These records are maintained in Alice and no other relevant discrepancies were noted. Okay, so I'm just thinking, is it worth me now making that system explicit in the control structure? Or should we keep reading and come back to it? I think that's what we should do. So maintenance procedures then. A landing gear fluid servicing maintenance action was completed on the 25th of January 2022 to comply with the 200 flight hour inspection required by the JTD. So JTD is the Joint Technical Data. This maintenance action is completed by depleting the pneumatic pressure as well as flushing the hydraulic fluid from the landing gear struts. To accomplish this task, the maintainer opens the swivel nut, releasing the nitrogen and hydraulic fluid from the strut low pressure port. The maintainer will then begin servicing hydraulic fluid in the landing gear strut, followed by pneumatic servicing. So hydraulic servicing and then pneumatic servicing. Hydraulic servicing will be complete when a bubble-free stream of hydraulic fluid is seen flowing through the clear tube that is installed on the swivel nut located on the low pressure nitrogen servicing port. Following hydraulic servicing, pneumatic servicing will be conducted by connecting a nitrogen service cart to the swivel nuts for the applicable high-low pressure pneumatic side of the strut. This maintenance action takes more than 2 gallons to fully service all 3 landing gear struts. Fantastic. 3 days prior to the mishap, so that's some time information that might be relevant. 3 days prior. I can't spell today. There we go. I can't speak, can't spell or write. Oh dear. Anyway, the maintenance team used no more than 2 gallons of hydraulic fluid to service the aircraft because the team only used 1 hand cart and they did not refill it during the procedure. It was determined that water was already in the struts prior to the servicing because of the amount of hydraulic fluid correctly serviced. Okay. So they use no more than 2 gallons. Okay. Maintenance personnel and supervision, both maintainers, so there were 2 maintainers. 2 maintainers. Assigned to the 355th Fighter. What was FGS? FGS. Oh, that's the ground squadron, isn't it? The FGS, that's the maintenance ground squadron. Where's FGS in there? Come on, FGS. FGS is missing. Found one. There we go. I think it's mentioned earlier on, isn't it? Let's have a... It was mentioned earlier on somewhere. Is it mentioned there? No, it's not. So FGS, what the heck is FGS? Flight Ground Squadron, something like... Yeah, it is. No, hang on, that's the one we've just been looking at. So what's FGS then? Anybody know in the chat what Foxtrot Golf Sierra is? FGS. I'm sure we touched on it yesterday. I seem to remember something. FGS. Come on. You know what? I could just try the search function, couldn't I? But of course it doesn't work. That's helpful. Right. That's not helpful at all, is it? Let's get the official investigation report open. And I'll search for FGS in there. There we go. FGS. Come on, where does it describe what it is? I'm sure it said it. It doesn't say what is FGS? Come on. Is it the ground squadron or something? Ground squad. Come on, what is it? Ground, 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 background. This is weird. I could have sworn. That's really strange. Okay. I'm going to have to search on Google. What does USAF FGS, what is it? Fighter Generation Squadron, apparently. Okay, yeah, which is responsible. You're not seeing this, are you? There you go. So, Fighter Generation Squadron, which is responsible for the inspection, general, and organisational maintenance of specific type of aircraft. Okay, so that's what it is. Right, there we go. Fantastic. So now we know what it is. There we go. So now we know what that is. Let's go back to where we were. Going too fast. There we go, sorry, FGS. So let's paste that in there so we don't forget. FGS. Oh, here we go, Milan. Hi, Milan. Great to see you, mate. FGS sometimes means fuel gas supply or flying ground service. That's thanks for that. That's really helpful. They're different acronyms to what I'm used to. That's what it is. That's my excuse, and I'm going to stick to it. Okay, so both maintainers were assigned to the 355 Fighter Generation Squadron. I'm sure that was mentioned somewhere earlier on. I'm misremembering. Who performed the service on the 25th of January. So that was 3 days prior. So they performed the service on the mishap aircraft. They were fully qualified, everybody. So that's fantastic. To do the required maintenance. The maintainers involved were a 5-level journeyman and a 7-level craftsman trained maintainers. So I presume that they're quite, high-spec maintainers. Fuel, hydraulic, oil, oxygen inspection analyses. So following the mishap, the ARFL, no, it's not right, is it? AFRL, tested the hydraulic fluid in the mishap aircraft's nose landing gear and right main landing gear. AFRL found that approximately 1/3 of the fluid retrieved from that was water. Wow. That's interesting. Let's mark that. Nice colour. Ouch. Approximately 1/3 of the fluid was water. Yeah, that's quite a lot of water, that. That is quite a lot of water. That's probably going to have an effect on the performance of the landing gear. Wow. That is a lot of water. 1 litre of water found in 2.8 litres of nose landing gear hydraulic fluid. 1.5 litres of water found in 4 litres of main landing gear hydraulic fluid. The hydraulic fluid was sourced from a barrel, in the 355th FGS support section, and serviced into the mishap aircraft with a hydraulic servicing hand cart. The barrel and the servicing cart were both tested for contamination following the mishap using a portable oil diagnostic system. The pod's use of SAE standards. All right, okay. So yesterday I said the mention of SAE was interesting, and I simplistically presumed it was related to the safety assessment process used as part of the design of the aircraft, which it is, but in this context it's about standards for hydraulic fluid. So I've learnt something new, fantastic. So standards for hydraulic fluid, and the test results showed that both the barrel and the hydraulic servicing cart failed to meet minimum standards for hydraulic fluid. Okay, so in terms of the control structure model for this then, so the physical process is essentially putting hydraulic fluid into the aircraft, into the landing gear. And so the control actions are provided by the maintainers, one or both of them, depending how they work together on the day. But of course, the actuators that they used are the hydraulic servicing cart, and of course the source material, the process input to that process is the hydraulic fluid inside the barrels. So there's a question then over, and obviously I haven't read the rest of the report yet, so I don't know what the answer is. I'm just thinking of what potential considerations we might have. But the physical process for the maintainers is putting the fluid on board the aircraft using tools and source materials. But then the next question is, well, who or what control structure is involved in controlling the hydraulic fluid in the barrels, and then involved in making sure that the servicing cart is tip-top and not potentially contaminating or damaging the aircraft. So I suppose I could start maybe drawing a new control structure for that. So let's just duplicate this. Let's get rid of all the scribbles, if I can remember how to do it. There we go. Delete. There we go, so that should be nice and clean now. There we go. So let's think about it like that then. In fact, let me get my iPad, because that's easier to draw with. Stand by. Miro, here we come. Let's have a quick drink while it's loading. Stand by. And I've just realised I'm muted and you can't hear me. I'm very sorry about that. All I was saying was just thank you for coming along. Please let us know what your interest is in the chat of what are you interested in terms of stamp, STPA and cast. And if there's anything specifically you'd like me to address as we go through this report, and if you have any technical expertise you'd like to share, please feel free to do that. So what I was saying is, what I would do is I'd call this controller on the left-hand side of the screen, maintenance team. Recognizing there's two of them, so there was a level 5 and a level 7. I don't know who was doing what, probably doesn't matter. But what they were doing is they were servicing the aircraft. Or what would they call it? Maintenance actions. Maintenance actions. And of those maintenance actions, hydraulic service, that's it, hydraulic servicing, and they used one hand cart. So if you imagine for a minute that there's a level of abstraction between the controller doing controlling things and making decisions, and then there is the physical process that they're enacting on. So in this case, their physical process was the mishap aircraft and its landing gear system. In fact, let me just zoom in on there so you can see it a bit better, make it a bit bigger. There we go. So the maintenance team, the level 5 and the level 7, they were providing hydraulic servicing, maintenance actions to the mishap aircraft landing gear. This yellow line represents the abstraction. So we know that they were using, 2 gallons of hydraulic fluid. So in terms of the process that they are, so they had 2 gallons of hydraulic fluid. They were using the one hand cart. They did not refill it. So in terms of refilling, they didn't do that. So it's whatever is inside the hand cart that is used as part of that control action. There was already water in the struts, so that suggests that previous servicing might have introduced the water, or the water has found its way into the struts through its own mechanism. I don't know the details. I'm not a specialist on this. I'm sure if you know, you can you can tell me. So the mishap. So they found 1/3 of water in the hydraulic fluid, which is quite incredible. The hydraulics fluid was sourced from barrel. So if I just move this over here a bit, so you can see 2 gallons of hydraulic fluid. That came from some barrels, a barrel. I'm drawing a box around it, not because it's a controller, but because it's a control process for somebody. So who or what is in control of that hydraulics barrel and the content? That is a control process. That's what CP means. Let me zoom in a bit so you can see it. So who or what is involved in that hydraulics barrel and the content of it? It mentions there that they use the hydraulic servicing cart. So I'm presuming that's what this is here, the hand cart. So hides, service, hand cart. So let's make that into a controller, and let's steal that bit, duplicate. So who or what is involved in looking after the hydraulic hand cart? There you go. So we've got potentially 3 control loops there to consider as part of our analysis. The barrel and the servicing cart were both tested for contamination following the mishap using the pods. The pods uses standards for hydraulic fluid, and the test showed that both the barrel and the servicing cart failed to meet minimum standards for hydraulic fluid. So both of these, oh no, not that one, this one. Both of these are not in a good state. And I'm just busy colouring in. There we go. I should have used boxes instead of drawing it. But yeah, so we know that those 2 processes, control processes, there's something not right with those. So the exploration of the investigation should essentially be, let's have a look at these control actions here and here. So why were they inadequate in making sure that the hydraulic fluid was not contaminated? Because that's really what we're focusing on here, the contamination of lac fluid. To that end, the barrel tested with more than 1,024 parts per million particulates. Why is it not? Oh, it's because I've got two screens open at once, that's why. I'm trying to be too smart, that's what's going on. Anyway, which is more than double, oh dear, more than double, 2x, the allowable limit for particulates in hydraulic fluid. The hydraulic servicing cart was also contained more than double the allowable limit in the tested fluid. It's important to note that the test does not accurately measure contaminants above 1,024 parts per million, so the contamination was potentially far greater than 1,024. Excuse me. Okay, so that's not good. That's not good at all. So let's explore. So this use of pods that we're talking about here. If I was to draw another controller up, actually, let me do it like this. Copy. No. Duplicate. Let's just put that there. Get rid of that. Is that still on your screen? Yes, it is. So let's just assume for a minute that this thing called pods. Let's just get rid of that arrow and that arrow. So there's this thing called pods that is used to collect information, do some reading. I can't draw on it, it's too big. Just bear with me a second. So there's two bits of feedback there, which is related to the use of the pods. PODS. So who or what is that organisation? And recognising that there'll be one for the investigation, because I think it was AFRL, or however they pronounce it, for the purposes of the investigation, they've checked the servicing cart and the barrel. But in terms of, I'd like to think that they're doing that kind of checking of the hydraulics and the cart anyway as part of normal servicing. So there's a question there about who or what is involved in the feedback path of making sure the fluid is appropriate. So this one here and this one here, the start cart, or is that responsibility, that explicit responsibility, actually allocated to whoever these are? I don't know who they are at this stage. And are they even the same controller? They could be the same controller. We don't know that at this stage. But that's the sort of, what I'm trying to show you here is by thinking about things through the lens of control loops, jigsaw pieces, it allows you to think, oh, actually, we've got this physical situation or we've got this control action. Who or what is involved in that control structure? And this is not about trying to find people to blame or anything like that. It's trying to understand, uncover, what are the jigsaw pieces? What is the jigsaw puzzle that we're actually involved in this particular situation? And so if we were able to interview these two, whoever those people are, presuming it's not AI and anything crazy like that, but who are those people? Are they the same people? What are their responsibilities? If they provided the control actions or didn't collect the feedback, why did it make sense? What's going on there? So I'm sort of jumping ahead a little bit there, but I hope that makes sense, the logic behind the thought process. Okay, so going back to this, so it's potentially more than 1024. Okay. That's some hydraulic fluid contamination table. Yeah, okay, I'm not really too fussed about the specifics of that. 355th Hazardous Communication Support Program. Okay, so that might be a controller of some description. The 355th Hazardous Materials Program, so HAZMAT program, suffered from insufficient manning. Oh, here we go. Insufficient manning and frequent supervision changes at times relevant to the mishap. Okay. So I'm presuming then that this red box I've drawn, this is what they would call the hazardous materials program. I'm assuming. And this is one of the advantages with CAST is when you identify a candidate controller, the first question, in fact, I'll just zoom out and show you. The first question is, for this particular controller, what are their safety-related roles and responsibilities and safety requirements constraints? If it is making sure that the hydraulic fluid is below a certain limit of contamination, then who has that responsibility? Why was it not fulfilled? And if, as this says here, there were frequent insufficient manning levels and frequent supervision changes, that would explain why it's not been done. But who's responsible for making sure that who is the person who decides on manning levels, or what department, and then who decides about supervision changes? Who is that layer above these ones? There's another layer there. Who's involved in that? Why did it make sense for them to make those decisions? Because there may be some genuine, we're not here to point fingers and blame people or, question people's competence. It's not about that. It's about understanding what are the facts, whether it's related to competency or not. What was the decision making? What were the beliefs? Why did it make sense? So airmen and non-commissioned officers were frequently swapped into the program, and at the time of the mishap, there was not a primary program manager assigned. Okay, there we go. That's interesting. So let's stretch this around a bit. Let's move this down a bit like that. So we've got a question there about, let's steal that bit there, not that, duplicate, let's put it over there. Let's get rid of all of that and the red bits and the red bit. There we go. So there's a question there over who or what. And maybe I'll stretch it a bit more. There we go. Put it down there. Okay. So who or what? So we've got the, you know what I might do? I might use a box. Where is it? There we go. Might make it look pretty if I do it like this. So the 355 Earth hazardous comms support program. Should have a program manager, so let's put that there, but there wasn't one. Okay. Additionally, HACOM. Oh, hazardous communication, I'm assuming. Let's just have a look at the acronym list. HACOM, HHH, missing. There we go. HACOM. It needs to go in there somewhere, and that needs to go in there somewhere. Okay. Where were we? There we go. Program managers did not lock the barrels. Okay, so if we're talking about the barrels down here, that particular single line there did not lock the barrels. That's related to this control action here. And then we've got, so that's a potential contributory control action. If we want to get technical. Observe servicing of hydraulic cart to ensure maintainers were properly servicing hydraulic or oil hand carts, nor log. So they did not observe servicing, so that's another contributory control action. And I suppose that's actually related to, let me use my pen over here. That's probably a feedback path Why is my pen not working? Come on. No. Where's it gone? There we go. Yeah, you can see my screen, so let's just move that there. So there's a potential missing feedback loop from there or there. It's not really clear from the description, but that's about observing the servicing of the hydraulic cart. Oh, right, okay, so that could be this control action here, or it could be another, or it could be this one we've already highlighted here like that. Could be that one that this is referring to. And there wasn't a log what hydraulic or oil servicing carts were filled from what barrels. So there was no log. So in terms of, if you imagine the, let's have a look, let's choose a different colour. If you imagine the beliefs or mental model of these people, whoever they are, if you can see that, or whoever this person might be, beliefs, mental models, the log, whilst the log is not a controller itself, it is a representation of the process model. Is a process model which is a representation of the state of, I'm going to make it even, yeah, it's a representation of the state of these two. So if there's no log, then, you know, how do these individuals or how does the organisation know and be able to manage and maintain and control that control process? Well, they can't, as we're sort of alluding to here. So I'm just going to quickly add that up here. So what's it called? It's called a log. So let's just make that explicit, because the log is important. It is really, it's not just paperwork, everybody. These, you know, yes, it's paperwork or, you know, digital, but it is critical information. And this is one of the questions. In fact, this is a good topic to talk about. So I mentioned yesterday, I'm doing some work on electronic prescribing medicine administration investigation. And there's always a question about whether it's a medical device or not. And in the UK, in Europe, there are regulations on how to classify medical devices. You know, certain functions mean it's definitely a medical device. And if it is, it has to be managed in a certain way. And if it's not managed in that more robust fashion. But the question is not, you know, whether it's a medical device or not in that context. It is, what purpose does that record, you know, the log in this case, what purpose does it serve in a control structure? And if it's not provided, it's lost or denied, or if it's too late, or it's provided out of sequence, or it's not consulted, does that have an impact on the overall control structure? Does that influence, perhaps dangerously, the behaviour of certain controllers? So in this case, it's obviously really important that we manage the amount of water in the oil contamination. So the log that supports that function is, you know, it's of a similar level of it needs to be a similar level of integrity. It has to be looked after and controlled. And if it's not, it's only a matter of time before an accident can occur. So, yeah, it's just a log. No, it's not. It's actually a critical part of the control structure. So I've banged on about that. So nor the log, what hydraulic or oil servicing carts were filled from the barrels. Moreover, the hydraulic pump that sits on top of the barrel had no Teflon thread sealer. So this is about a physical, you know, we're talking about the physical process here, and how, sorry, let me use my pen over here. There we go. So if this is the hydraulics barrel in the content, and you have a process to refill it, using, what's it called? Using a hydraulic pump. Okay. And that has no Teflon thread sealer, which could permit water to contaminate the hydraulic fluid if the barrel was not stored properly. So this is where we focus from a physical process perspective. This is where we'd focus. Well, was it supposed to have a Teflon thread sealer? If not, why not? You know, what's the controller involved in that? Is it a design issue? Is it a maintenance issue? Is it a build issue? Did it come from the factory with this part missing? So is it a manufacturer issue? Is it a maintenance issue? And then, of course, water getting in to contaminate the hydraulic fluid if the barrel was not stored properly. Okay, so again, that goes back to this controller. Who or what is involved in maintaining and storing the barrels? You know, what decision making did they make? Was there a conscious decision to store it in a particular place which was not stored properly, whatever stored properly means? Do they know what criteria they need for proper storage? Because if they don't, that might explain. Or again, what's the broader context of the control structure? We mentioned yesterday that the Air Force Base, they might be a candidate for inclusion in the control structure, perhaps, and we don't know yet because we've not got to it, but perhaps the airbase said that they've only got certain facilities available, and perhaps it's only outside, so that's where these things were stored. You know, I'm just sort of postulating ideas to try and stretch your perspective of what type of things you might want to consider including in your control structure model. Okay, so let's just have a quick look. So permit water. Oh right, here we go. Here's a nice picture of it. Look. Okay, so you can see the corrosion on this barrel. Looks a bit beat up. Yeah, there's no sealing on there. You can see. So the question is, who fitted this? Because I'm presuming they don't come from the factory like this. Before I saw the picture, I'd got a view in my mind that's not appropriate. So now I've seen it. It seems that this pump is removable by the staff using the barrels. So you'll roll the barrel into place, fit the pump, and crack on with it. So why would it make sense for the person who did that to not include a Teflon thread sealer? There we go. Maybe they didn't have any. Maybe they didn't have any in stock because there's an issue with the supply chain for those things. And if that's the case, what does the supply chain control structure look like for that seal? I'm going a bit crazy here. I'm just trying to stretch your mind a bit. Additionally, there was insufficient tracking of what hydraulic barrels went on movements and whether said barrels returned to Ilson. So there's a tracking aspect. So let's have a look. Come on, wake up. That's it. So I put a log over here, look at the top, and there is an equivalent log needed for the barrels themselves. So status of the barrels and then status of the maintenance and content of the handcart and the barrels themselves. And those two logs, this one up here and this one down here, they could be part of the same logging system, maybe. I don't know. I'm guessing. That might affect the way I model the control structure. Because there was that mention of that Alice thing earlier on. Let's have a look. Where is it? Alice. Where are you? There we go, Alice. So is Alice relevant to this? Is that the log that they're supposed to use? Is that the log that's supposed to track and manage the... so it's about servicing, inspections, aircraft configuration, statuses. I don't know, maybe it's relevant. I mean, that raises a question. Alice containing that level of information, because of the type of information contained, it should be a good level of integrity, that system, that software, the interfaces. And if it's not, then that could cause lots of problems and have huge consequences for everybody across all aircraft. Anyway, information pertaining to barrel movement is not required to be tracked in depth, but hazmat records were incomplete and did not permit accurate tracing. For example, information about the 354 FGS hydraulic fluid barrel that was transported to Kadena in support of a theatre security package was overwritten by a subsequent deployment to that airbase. This error made it impossible to track where the barrel had travelled upon completion of the exercise. Okay. Yeah. Okay, that's interesting. Because of incomplete records, there was insufficient information to confirm whether the barrel used to service hydraulic fluid on the 23rd of January was the same barrel that was left outside in inclement weather. Ah, okay. For at least 6 weeks. This was in direct violation of it. All right, we'll come back to that. So, because of incomplete records, there was insufficient information to confirm whether the barrel used to service hydraulic fluid was the same hydraulic barrel that was left outside in inclement weather. So in terms of this control structure then, I was thinking that it was constrained to Eielson Air Force Base. But what this is describing is actually this barrel was actually under the control of somebody else in a completely different country, in Japan. So that's interesting. This was in direct violation of Air Force regulations. Okay, so Air Force regulations would be higher up in the control structure. In fact, I'll just scribble those on there just to sort of add a bit of detail. Bear with me a second. Air Force regulations. So the question is, how does that get down to the person filling the barrels, or to the persons that are involved in maintaining them, looking after those barrels and moving them around, and the logistics and all that kind of stuff, which require the hydraulic fluid to be stored in a container. So the fluid is to be stored in a container, tightly closed in a dry and well ventilated place, because it's quite nasty stuff. You don't want to be breathing it in accordance with AFI 91203 and OSHA safety data sheets. Additionally, the hydraulic barrel that was used to service the MA had been marked empty, consumed in April 2024, but had not been disposed of. Even so, it was in use and, when tested, contained about 33% water. Okay. So there's a whole consideration of the control structure for that physical process, which is the barrels, the content of the barrels, and the hydraulic service cart. And then, of course, the feedback loops to control that process and make sure it's adequate and make sure the aircraft is not being fed with contaminated hydraulic fluid. Great. Okay, well, I think that's a good point just to have a quick break. So I'm just going to have a quick 5 minutes to have a drink and get refreshed. And then I'll come back and we'll carry on, do another hour or so and see where we get to. So thanks for your watching, and I'll see you in a little while. Take care. And we are back, everybody. Hopefully you can hear me okay. Fresh cup of tea, all rearing to go. Right, have we got anybody in the chat? Here we go. Ashley Craig. Hi Ashley, great to see you. Thank you for coming along. If documentation was incomplete, would it have made a difference if they were complete? And would they have been reviewed as we already know the pump was not installed correctly? That is a good question. That's a fantastic question, actually. If the documentation was actually complete, would it have made a difference? I suppose the question for the investigation is, what control was there over the installation of those? Of these pumps? So, was somebody actually in place to assure? Were they actually responsible for? And know that they were responsible for fitting these things properly? And is there someone else who is responsible for checking? And what sort of check is it? This is a common theme, the concept of a double check. Is it that we are checking somebody's beliefs? Have you, a person A fits the pump, person B checks. Is that check literally, hey, person A, did you fit the pump properly? Yes or no? Or is it literally going and checking that the pump has actually been fitted properly and in accordance with the procedure and with all the parts necessary? What level of checking is done? What level of checking is necessary and required? And I'd argue that, given that contaminated oil bringing an aircraft down and wasting $196.5 million, you would expect that the check and the control structure that puts that check in place is appropriately, proportionally robust. And clearly not in this case. And I do wonder if this is the same across the entire Air Force, across all Air Forces across the world, across all maintenance facilities that have to do hydraulic servicing. You know, maybe there's a learning point for everybody here. What is your control structure and the control structure for checking, independent checking, that you have in place for, you know, dealing with hydraulic contamination? I hope that answered your question. I think the answer is, you know, it depends on whether the documentation is designed in combination with people's responsibilities and how those responsibilities are allocated to a control structure. And if you don't have a control structure because there's not enough staff, or, you know, people get moved around and their responsibilities may not be made explicit, then it's kind of inevitable that something like this could happen. So there's a lot we can learn from this. It seems really basic and straightforward, but there's a lot from a control structure perspective that we can learn from this. Fantastic, thanks Ashley, I really appreciate that. Right, okay, let's keep going. So the February the 6th, 2025 incident. February the 6th. I thought we were talking about an accident in January. I'm sure we were talking about an accident in January. Let's have a look. Date of accident, 28th of January, so 6th of January. Does this mean there's another incident? Oh, I should maybe just read it, shouldn't I, instead of trying to guess. A similar incident to the mishap aircraft occurred 9 days later. Bloody hell. When another F-35 from Alson experienced a landing gear malfunction on takeoff, that aircraft experienced a nose wheel gear unsafe indication after takeoff, and after following, the gear failed to retract. Checklist, the pilot lowered the landing gear and flew for approximately 40 minutes before landing uneventfully. Thank God for that, bloody hell. Excuse me, post-flight analysis indicated the unsafe nose gear indication was due to the up lock missing the roller and rotating the nose wheel 10 degrees to the left in a similar manner to the mishap aircraft. So is this a different type of accident? Does that mean there's been a maintenance issue with the landing gear, not to do with hydraulics? So the outcome is similar, but the causes are different. While landing, the maintenance data showed the nose wheel went from 10 degrees left to 5 degrees. Neither the pilot nor the wingman noticed. Blooming heck. So the question there, is it that 5 degrees is survivable and doesn't flip the aircraft upside down? And if it had stuck at 10 degrees, would it have flipped the aircraft upside down, but the pilot would not have realised? I mean, these are things you wouldn't expect the pilot and wingman to be having to check the gear after takeoff before retracting it and then making sure it's clear after retraction every time. But then I'm not a fighter jet pilot, so they may do a lot more checks than I anticipate. You know, it's an aircraft, it's not a car, Simon, you know. There's a lot of things that you'd have to check that you wouldn't do on a car. Anyway, a post-flight test was done on this aircraft by first towing it into a climate-controlled shelter. What's 70 degrees? 70 degrees American into English, so 21. So it's quite a warm 21 degrees, quite balmy t-shirt. And recording the nitrogen pressures on the landing gear shock struts, the aircraft was then towed outside where temperatures remained below 15. So 15 is -9, so that's still cold. Still cold. But not as cold as the previous accident. I can't remember what that was. That was like -7 or 11 or something. Where is it? Where's the temperature? I'm sure I scribbled it down. There it is. No, yeah, there we go, -17. So it's -17. Yeah, so it was not as cold as the previous one. So And yeah, okay. After 12 hours outside, the aircraft was jacked up until all landing gear cleared the ground. Measures were then taken of the landing gear struts. The aircraft's landing gear failed to reach full extension when the main landing gear struts failed to fully extend. The WOW switches cannot physically extend and do not function properly. Oh dear. Temperature was taken of all three struts, which measured 14 degrees. 7 degrees to the left main, a right main. The aircraft, oh, that's interesting. So the main gears were warmer than the nose landing gear. The aircraft was then lowered and towed back into 70 degrees climate control hangar, sat for 12 hours. All three landing gear struts were then drained of all fluid into mason jars. The nose landing gear, left main landing gear had a significant amount of water present, while the right main landing gear appeared to be all hydraulic fluid. So for this particular aircraft, does it give a tail number? Yeah, it doesn't say which other aircraft it was. So it's obviously it's a different aircraft because the first one's been smashed up. The subsequent incident and test replicate the same conditions that the mishap aircraft was experiencing. The presence of water in the landing gear struts during below freezing weather conditions did not allow the gear to fully extend in either aircraft. Flight records show these two aircraft had previously flown in the days prior to both incidents without experiencing this malfunction. During those sorties, the ambient temperature was not as cold as the day of the mishap. Additionally, the time spent during ground operations, time between leaving the heated weather shelter and takeoff, was less than both the mishap aircraft sortie and incident. With that, it is likely that both aircraft flew sorties with water in the landing gear struts without malfunction, since the water did not have time to freeze before takeoff and gear retraction. Yeah, okay. Unscheduled maintenance. There was no unscheduled maintenance relevant to this mishap. Great, fantastic. Okay, section 6. So let's just quickly go back to these table of contents. So we've done that, and we're down to here. So we've got section 6, 7 and 8 to go. So I think section 6 is going to be most exciting, so let's carry on with that. Section 6, structures and systems. Prior to the mishap aircraft was partially mission capable due to issues affecting systems that were not relevant to the mishap. Partially mission capable. The mishap aircraft showed no major issues and worked as described, aside from the landing gear and related systems that will be discussed below. Okay. So what we're sort of saying there is the aircraft was serviceable and fully safe to fly, apart from the issues with the landing gear. And it's quite interesting to sort of think from a system safety engineering perspective and what the aircraft safety process is all about. And I'd probably argue that most of the safety related work from a landing gear perspective is all about making sure it retracts and extends. And what am I trying to say there? I'm trying to say that simplistically, it seems that contaminated fluid brought the aircraft down, but there's more to it than that. It's not just landing gear. There are other things that conspired together to lead to loss of the aircraft. And I suppose when we get through the rest of this section, it'll become apparent how the landing gear system safety assessment and how the aircraft safety assessment might want to be perhaps reviewed, how they interact with each other, what are the common modes, common causes perhaps that need to be considered. because this is not straight. It sounds like a straightforward accident, but from a system safety engineering and an aircraft safety design perspective, this is subtle but quite complex. So the landing gear system is a tricycle design consisting of the main landing gear and the nose landing gear, extension and retraction, wheels and brakes, nose wheel steering, position and warning, and arresting gear. So that's a hook typically at the back. The nose landing gear up-lock hook is used to ensure the landing gear assembly is up and locked appropriately. The up-lock is mechanically slaved to the nose landing gear door. The nose landing gear is in the up-lock, so the nose landing gear door actuator will start to close the door, raising the up-lock hook into the locked position. When the up-lock hook is in locked position, the doors are closed and the aircraft is ready for full flight envelope. Oh, sensor, there we go, that's important. And then the target for the sensor. Spring strut, gear up-lock hook, upper push rod, crank arm, lower push rod, door hinge. Fantastic. Okay, what's this one then? So this is the nose landing gear lower shock strut. So we've got lower centering cam, possible ice build-up in the area, upper centering cam, upper shock strut. The nose landing gear centering cams are used to ensure proper centering of the nose landing gear. One of the cams is mounted at the top of the landing gear strut and the other is mounted at the bottom. At the beginning of the mishap flight, the nose landing gear didn't fully extend due to ice build-up within the strut. The ice build-up was the combination of significant water contamination in hydraulic fluid used to service the struts and ambient freezing condition temperatures around Elson. The lack of full extension caused a misalignment that prevented the nose landing gear up-lock hook from catching the nose landing gear up-lock roller, causing damage to the metal adjacent to the roller. Ah, okay, there we go, look. So we've got some damage. Okay. Additionally, significant pitting was identified within the landing gear piston that, while caused by contamination to the hydraulic fluid, did not affect the landing gear function. Okay, so that's interesting because in terms of servicing, so this is, I just move this over here. In terms of feedback there, you've got the pitting within the piston. So I'm presuming that the maintenance procedure or servicing procedure will look for those signs, because if it's left to get worse and worse, you'll end up with potential cracks and perhaps, pressure release or breakup of the piston itself, which would be bad. I'd imagine that takes a while to happen, so that you might have a dormancy period. I'm assuming that. I'm sure there's people out there that know everything about landing gear and have done the failure modes and effects analysis for these components, and have they understand the physics of failure associated with ice and water contamination. Okay, so some nice pictures. We've got the nose landing gear, the main landing gear, and the WOW sensors, weight on wheel sensors. I'm impressed with this. One of the things I really like, you can tell that whoever's been involved in the investigation has got a real good sense of attention to detail and also a healthy respect for the audience when they include descriptions like that to help you visualize in your mind, tell a story about what you're actually looking at. I really appreciate that, whoever wrote the report. Thank you. After the nose landing gear uplock hook missed the roller, the nose landing gear was forced left 17.5 degrees, leading to the in-flight emergency and multiple touch and go attempts. After the first touch and go, the right main landing gear and nose landing gear wow sensors showed weight on wheels, despite the aircraft being airborne. This was because the aforementioned ice buildup prevented the struts from fully extending or retracting. On the last touch and go, the nose landing gear wheel went from 17.5 degrees to 6 degrees after it was allowed to briefly touch the runway. So just quickly, just to emphasize this previous accident that occurred. This one here, similar accident. So they said that it went down to 5 degrees at touchdown, whereas this one was at 6 degrees at touchdown. Is that suggesting, and please entertain the idea, is that suggesting that with the accident aircraft, the mishap aircraft, if they'd have tried to land with 6 degrees, after this touch and go, the aircraft might have survived, because we've got circumstantial evidence here that this other aircraft landed with 5 degrees at touchdown. So maybe 6 degrees, maybe they get away with it. I don't know how hairy 5 degrees was. But of course, that's an academic question because, after the aircraft took off again with 6 degrees, we ended up in an uncontrolled situation. So, yeah, a bit of an academic question now, I think. Pitting identified... Oh, that looks quite bad, actually. That looks quite bad. Pitting identified in main landing gear position. Piston, should I say. As discussed below, the inability of the strut to fully extend and retract impacted the proper functioning of the wow sensors and the flight control law on the mishap aircraft. According to Lockheed Martin, if a main landing gear strut fails to fully extend to the predetermined length, then the wow sensors cannot extend and will report weight on wheels. So in terms of thinking about the control loop, so I'll just quickly jump back to this one here. So have we put wow sensors on there? No, we've not, because this is the pilot and this is the aircraft. Okay, so this yellow line just to represent the abstraction between the aircraft as a control process and the pilot. What I might elect to do is add... Let's stick another controller in here. Let's have landing gear. I can't spell. Landing gear. Excuse me. There we go. And then let's make that text a bit bigger. There we go. Make the box a bit bigger. That's it. And then, oh, no, I didn't mean to do that. And then this can be the wow sensors. WOW sensors. So that box represents sensors. That doesn't represent a controller. That represents sensors. Just to sort of, emphasize that point. And of course, we want an arrow, so let's get an arrow that goes from there to there. Let's make it a straight one. There we go. Oh, no, I didn't mean to do that. There we go. So we've got wow sensors. So the wow sensors provide feedback to, in fact, actually, let's just do this as well. So the aircraft controls its landing gear to command it up and down. The wow sensors provide information back to the aircraft, and the aircraft decides what state it's in. So let's have a look at this then. So yeah, that's a really important point just there. There we go. I'm just going to grab a drink. Just bear with me a second. There we are. Back again. Right. So the weight on wheels sensors. Let me just zoom in on there so you can see it a bit better. So the weight on wheels sensors are one component of the F35's flight control system. So what I'm going to do is I'm going to make a box that says flight control system, FCS presumably, and that goes into the FCS. So I'm just going to make that, I'll just move it down a bit actually. There we go. There we go. Hope that makes sense. Each main landing gear has 2 wow sensors. So if I want to get exciting, I could probably put, what is it? MLG wow sensor times 2 and each. So I could put left and right times 2. There we go. So there's 4. And then what else is there? They're mounted on the shock strut. And then these sensors, along with a single wow for the nose landing gear. Nose landing gear, wow. Sensor times 1. There we go. So we've got 5 sensors. So if you've got a fault tree analysis, it's going to look fantastic because you've got 5 sensors, everybody. So 2 wow sensors and a single wow are part of a redundant system, everybody. It's redundant. That is intended to function even when multiple sensors fail. But we're not talking about sensor failures here, are we? Or are we? Good question. When the shock struts are fully extended and then compressed by the weight of an aircraft, the wow sensors are designed to reflect that the aircraft is on the ground. Both main gear wow sensors are plunger type sensors, actuated by keeping physical contact with the landing gear torque arms integral cam. So let's have a look at this. Oh right, okay, that's interesting. That's how it works. So there's a cam that moves, which essentially moves the sensors. I shouldn't say sensors, should I? They're switches. They are sensors, but they are switches. So that moves up and down. And there's 2 of them. Because the fault tree said it would be a good idea to have 2. Okay. Guessing. And they're actuated by keeping physical contact with the main landing gear torque arms integral cam. So it should be a really robust, really strong indicator of whether the aircraft's on the ground or not. Interesting. I wonder if this aircraft's got radar altimeter or accelerometers. Anyway, I'm guessing on the aircraft design I shouldn't be. So weight on wheel at the nose landing gear, switch, Hall effect. Oh, it's a Hall effect sensor. Fantastic. Everyone loves a Hall effect sensor. Is not aligned. Weight on wheels. So this is a diverse type of sensor compared to the other ones. And if I remember correctly, they're not that reliable. I could be wrong. Correct me in the comments if you know about Hall effect sensors. In fact, let me just. No, I don't need to add that detail. I don't need that level of detail, do I? No, I'll leave it. There's no landing gear switch. Is a Hall effect sensor actuated by the upper torque arm. The magnet side of the sensor must be within a predetermined distance from the sensor for the aircraft to recognise weight off wheels. So this one is I'm presuming this is weight on wheels because it's compressed, whereas this one is weight off wheels. So this is off and this is on. Weight on wheels, and then this one is weight off wheels. You might be thinking, Simon, why is that relevant? Well, it is a different functional logic. If you've got a sensor that's designed to provide feedback about weight is on wheels, and you have a different diverse sensor to signify weight off wheels, the way that those two bits of logic actually find their way into the control system is really important. What's the word? It's not geometry. There's another word, I can't think what it is, but essentially you need to make sure that logically the people involved in the aircraft design or the design of this system and the way they do the safety assessment, we're all humans, we're all prone to making mistakes and misunderstanding or misbelieving things and acting in ways that are not appropriate. We're all humans, part of the design process. Something as simple as the logic between off and on, that logic must be translated into the analysis, into the design, into the requirement spec. It must come out the other side and influence the way that we do verification and validation and testing, and then even down to the design of the way they build the thing and maintain the thing and how they do validation tests, verification tests, once the thing has been maintained. And if we, connect the thing the wrong way round or get the logic the wrong way round, we could find ourselves with a faulty design, potentially, that says that it's a safe design when actually it's not, or we could end up with a thing that's been built or maintained that seems to be safe, but actually the logic is potentially dangerous. And I'm not saying that that's what's happened in this case. I'm not saying that's what's happened in this case. I'm just saying that, we have to be mindful of these real small, subtle details and how they propagate through the safety assessment, the design, the requirements, even down to the details of a state machine diagram, for example. And I imagine that the safety assessment for the aircraft flight control system, including these, should consider the state machines and how state transitions occur. And if they haven't, that's potentially a recommendation. So let's just jump back into it then. So there we go. So that's a weight off wheels sensor. So 4 sensors from the mishap aircraft were tested who found they were functioning within specifications. So they've not failed, strictly speaking. Where was it? We were talking earlier on about failure. There we go, this bit here. Multiple sensors failed, so they've not failed. They've worked as designed. It's something else that's not worked. Dangerous success. Okay, so they were functioning within specification. Fantastic. However, this testing did not account for whether the WOW sensors would be able to function if the shock struts were not properly extended as a result of ice buildup within the shock piston. So if I was investigating this, I'd be getting the failure modes and effects analysis out for the struts, and I think I said this yesterday, and exploring to find out whether this scenario was included in the FMEA, and if it's not, I would make sure that it gets updated and ripple across the safety assessment. But of course, this is the same for every aircraft, all aircraft, I'd argue, anything with landing gear struts like this one and that arrangement of sensors. Anyway, yeah, I'm sort of digressing there. There we go. So let's just have a quick drink. Now let's talk about the flight control law, or the CLAW. F35A is controlled by execution of a defined set of algorithms known as CLAWs. Oh, fantastic. So if we look back at our You know, whilst this picture here shows decision making, this bit here, if you're familiar with the stamp literature, that represents the control algorithms, the decision making for that controller. So if we're talking about the flight control system down here, which we are, the claws, they are effectively the decision making control algorithms, which for this particular controller. So this is the claws. So let's just make that box a bit smaller, make the text a bit smaller. There we go. Fantastic. Let's make this box a bit bigger. We'll put the writing over there. There we go. That's fine in it. So we've got flight control system, decision making, control algorithm, clause, and logically we also have what's called the process model or beliefs process model. Oh, there we go. So I put a B there to remind you that it's beliefs, and a DM there to remind you that it's control decision making, and then of course it's control algorithms, process model, beliefs. There we go. So the sensory feedback logically goes into update the process model for the flight control system. So it's essentially telling the flight control system, hey, we're still on the ground, or we are on the ground, so behave accordingly. And then it's up to the control algorithm, the decision making of the flight control system, to decide what to do with that information. So the F35A clause include power approach for takeoff and landing, up and away, and on ground. So there's 3. So let's just make that. So power approach. I'm not going to remember that, so I'll not use an acronym. There we go, PA. What's the other one? Oh, what was it? Up and away, up and away, which was UA. Can't spell. There we go. And then the third one was, what was it? On ground. OG. There we go. So that's 3 different control algorithms that we're talking about there. Oh. So that's what they are there. I'm just going to leave them there. I'll tidy it up later on. I don't want to spend too much time doing that now. I'll tidy it up later on. Okay, so the PA claw, the power approach claw, is selected when airspeed is less than the programmed airspeed or when precise control of the aircraft is required. Excuse me. The OG, on-ground claw, is selected when 3 of 5 wow sensors suggest there is in fact weight on wheels, because the aircraft's weight has compressed the extended strut while on the ground. Okay, so that bit there is really important. So we've got, out of this logic, use my pen, there we go. Is it that one? Yeah, this one. Let's just zoom in. So we've got, let's use red this time. So this is saying that 3 out of 5 weight on wheels. So 3 out of 5 is weight on wheels. There we go. 3 out of 5 sensors. Recognising that nose landing gear 1 indicates weight off wheels. So if it's going to indicate weight on wheels, that means that the nose landing gear should have compressed. So nose touchdown. Yeah, there's various scenarios that would represent 3 out of 5. I'm not going to go into binary logic of it and do a truth table. If an aircraft is airborne but still on the ground, claw, it will experience significant degradation in flying qualities and loss of control can be expected. Okay, so it's quite important that this thing knows. On ground algorithm is pretty hazardous if you get that when you're in the air. Pretty dangerous, we'd say. $196.5 million dangerous, times by all the F35s that have this architecture. This is because the claw software is designed to provide the desired aircraft response rather than direct control by the pilot. Okay. So what we're saying here is we've got the flight controls. Yeah, you should be able to see that. So what we're saying here is this: the flight control system, if it is in ground mode, on ground claw, when it's actually in the air, the physical process is the aircraft is in the air, that can lead to controllability issues. Whereas this is because the claw is designed to provide the desired aircraft response rather than direct control by the pilot. So if this, this diagram's, I need to update this diagram. It's not appropriate anymore. I need to put this. They need to go there somewhere. That needs to touch the aircraft itself. So let's just name that mishap aircraft. Doesn't matter the detail, what type of aircraft it is at this stage. So let's just make that box represented there. Can you see that okay? Let me just make the text a bit bigger. There we go, mishap aircraft. And then we'll connect flight control system to the aircraft. That one there. Then of course that can go on the bottom of there like that. Okay, so the WOW sensors, yeah, it looks a bit messy, that, doesn't it? I think that's a bit too messy. Let's just move. There we go. This is what happens when you're doing these kind of analyses. It is an iterative process. So you have to, the more experience you get at building control structure models, you wouldn't make the mistake I've just made. I should have started with boxes on a diagram in the first place instead of trying to be clever about it. Story of my life. No. There we go, 3 out of 5 weight on wheels, there we go. So the flying control system controls the aircraft, but the pilot also controls the aircraft. So you've got, there goes the pilot up there. So the pilot can provide control actions to the aircraft, but then the flight control system can also provide control actions to the aircraft. So potentially there is a conflict of control actions there going on, but the diagram you've got there, the control structure you've got there, is implying that the pilots have direct control over the flight control surfaces, whereas it might not actually be the case. It may be that the pilot actually provides inputs to the FCS, and then the FCS decides what the control outputs are to the flying controls. So does that make sense? You can have two different architectures there, and it's important to recognize that. And that's why this process is an iterative process, because when you're developing the control structure model, you might not know that that's the logic. You'll have the implied logic, which is this, but the actual architecture is it's a bit more complicated than that. Actually, the pilot's inputs don't go to the flying controls, they go via the FCS. There might be emergency or reversionary modes, I don't know, but it is an advanced jet, probably not. Okay, so loss of control can be expected. This is because the claw software is designed to provide the desired aircraft response rather than direct control by the pilot. So yeah, that's think we're getting to it now, everybody. I think this is where the issues lie. When the mishap aircraft went airborne following the second touch and go, it remained in the OG control law, and control of the aircraft was not possible. Okay. So yeah, just to summarise that then. So looking at the control structure model, you've got a number of things going on here. You've got the clause that decide whether the aircraft is in power. In fact, actually, let me just make that explicit. Claw decision-making algorithm. It's actually 4 algorithms there. So there is an algorithm for deciding what control law to put the aircraft in. And then there is the actual algorithm itself, and the algorithm, what that capability means in terms of control actions of the flight control system. So if the flight control system believes the aircraft is on the ground, then it's going to use those control actions. So however it is possible for the flight control system to believe it's on the ground when it's actually not, that is going to cause the same accident. It's going to cause the same uncontrollability and the loss of aircraft. And I'd argue that that is a systematic design. Well, that is the design of the aircraft, apparently, according to this. So this feedback path, the weight on wheels, or the way that we design the aircraft to decide whether it's in flight or on the ground, is critically important for this flight control system. And I would wonder whether there is an override switch, for the pilot to set, yes, I'm on the ground, or no, I'm in flight. I don't know if that's a feature. Probably not. But let's say you've got a landing gear. Let's say you've got a landing gear failure. Maybe your landing gear's fallen off, or been shot off, or blown up, or something. You've got battle damage. How do you get the aircraft back to land on the ground? What happens if you get damage? A bird strike in flight or something like that causes the aircraft to believe it's on the ground when it's not. As you saw, it was within a few seconds from the aircraft is flying to out of control and crashing. So the pilot hasn't got much time to detect and respond to something such as that. So this is not good, not good at all. So the flight control system brings together systems to provide control of various parts of the aircraft through the vehicle management computers and the hydrostatic actuators in each flight control system. So if we were to, let's just make the model a bit bigger. I'm probably adding too much detail now, so we've got. I'm probably going to add too much detail now. I don't want to go too crazy. Maybe it's a bit late for that. So bear with me a second. So we've got the vehicle management computers, VMC. I can't spell. There we go. Vehicle management computers, and we've also got the hydrostatic actuators, EHA, in each control system. So there's probably multiples of these for the pitch, yaw, roll, and thrust, perhaps. I don't know. So I'll just chuck those in there. They are involved in that control actions in some shape or form. And the pilot is involved in that either through the flight control system or perhaps directly to the VMC or the EHA. I don't know if there's a reversionary mode, emergency mode, for example. Okay, right, let's keep going. So crash survivable memory. That's really interesting. Is that all they've said about the flight control system? That's it. Surely there's more. No, apparently not. Okay. Interesting. Let's keep going. And we'll call it a break at just before operations and supervision. We'll stop there because we've been going for quite a while, I think. What time is it? Nearly 1 o'clock. So nearly 2 hours, everybody. I think I'm hoping so far you're kind of getting the idea that perhaps this investigation hasn't gone far enough into the flight control system and the design of the aircraft. Why is it appropriate that we've got those kind of sensors that then cause the flight control system to decide it's on the ground when it's not, and then basically crash the aeroplane? That doesn't seem right to me, that. Anyway, let's carry on. So crash survivable memory unit is designed to survive a catastrophic crash and acts as a flight data recorder. Black box, fantastic. The CSMU from the mishap aircraft was retrieved successfully. Brilliant. CSMU begins recording data when the integrated power package is started or when external power is applied to the aircraft, and records continuously throughout the mission. Brilliant. Health reporting code issue. Lockheed Martin released a maintenance newsletter. They're not on the control structure model, are they? Let's just put that over here. So, aircraft designer, manufacturer. So they provided a maintenance newsletter in April 2204 that discussed main landing gear WOW switch faults. Okay, so there's somebody there knew about switch faults. So let's I hope you don't mind how scribbled it looks. It will look nicer than this next week, I promise. Maintenance newsletter. Before I go into the detail of this bit, I just want to emphasise something from a cast accident perspective. So you'll recall from what I said yesterday, cast analysis has 3 broad parts, and they're not sequential. They could be sequential, but they're typically iterative. But as part of the structure analysis part, the third analysis element, this part here, I mentioned the other day about this thing called a Safety Information System, SIS. Now, this looks like a really formal sort of system, and it could be, but it doesn't have to be. And it could literally be somebody providing a maintenance newsletter. Hey, everybody, for awareness, this is what's going on. You might want to be aware. And that is a way of making people aware of things, but if that is a safety piece of information, it should be communicated in a way that everybody who needs to know gets to see it, and they can acknowledge that they've read it, understood it, and taken appropriate action. So this is where we go from an informal to a formal safety management system, an informal to a formal safety information system. So I'll just quickly jump back to that. So we're going back here. So they provide a maintenance newsletter. Let's have a look. Let's take an arrow. Let's have that one. Copy, paste. So the aircraft manufacturer provides a newsletter in April 2024. So this was 10 months before the accident, 9 months, 8 months. The WOW switches on the main landing gear are a mechanical plunger switch that are known to have a history of failure due to internal damage. These failures assert as actionable health reporting codes and become more frequent during extreme cold weather operations where aircraft are prepared for flight in a climate control hangar and take off 20 to 40 minutes after being exposed to outside ambient conditions. Faults should be taken as early indication of landing gear failure. If an actionable HRC is asserting noting a fault to the main landing gear WOW switch, the AFRS tied to the HRC must be followed. So can everybody remember what AFRS is? I can't remember. I think we looked at it yesterday. Where's the acronym list? AFRS. It's not in there. How am I supposed to what it means? AFRS. Bloomin' heck. Right, let's look at the report. AFRS. What does it mean? Don't tell me it's only in there once. It's in there once. USAF What's an AFRS? It's not the Air Force Recruiting Service. Gosh. What is it? Can anyone tell me in the chat what AFRS means? I thought we saw what it was earlier on, but obviously we didn't. There we go. AFRS tied. I don't know what that is. What is it? What is AFRS? What is it? I can't remember. Must be. I'm presuming it's some kind of procedure, maintenance procedure or something, immediate action. I don't know. Not acting on a WOW switch fault could result in WOW switches faulting on a future flight, which can cause erratic flying qualities. Erratic? I'm not being funny, but something as serious as that is really serious, because we've lost an aircraft. The newsletter identified HRCs relating to the... Sorry, I just need to highlight this because that's just a bit ridiculous, I think. So this is interesting because it suggests that the way the aircraft designer manufacturer manages these issues and tracks them, do they appreciate how serious it is? Do they recognise how serious it is? I'm sure that they do, but this doesn't seem to give me the confidence that they really understand the potential risk of losing aircraft due to these issues. And I suppose before the accident, with hindsight bias, before the accident, they wouldn't have known that having issues with ice could contribute to this. Oh, we've got some people in the chat. Oh, Andrew. Hi, Andrew. Great to see you. Thanks for coming along. What's Andrew saying? So Google suggests the Spotlight tool used for AFRS provides off-board troubleshooting for F35 maintainers, capture maintenance knowledge and shares it across. Oh, wow. Anomaly and failure resolution system. Oh, Andrew, fantastic. You can come again. Thank you for that. Let's document that then. So AFRS brackets. Andrew, would you like a job? You can come and give me a hand. Where is it? Anomaly and failure resolution system, AFRS. Already done that. Oh. Right, so we can stick that there. We know what that is now. Let's make the text a bit bigger. And let's copy it over here somewhere. So there's this thing called an AFRS that somebody needs to use. I think we need a bit more clarity on what that is and how it fits into this, because, and like I was saying earlier on about information systems. Sorry, I'm drawing stuff and you can't see it. Sorry, I've just added this here, and then I've added it in here over there just to sort of stick it in the control structure because I think it's important from a broader safety management perspective. It's an important feedback path. What was I saying? So, yeah, so the newsletter identified HRCs. Oh, I can't remember what HRC is. Blooming heck. And it's missing from HRC. What does it say in the report? Everybody, HRC. Health reporting code, that's it. Health reporting code issue, there we go. I'm sure there's an easier way to do this. I'm sure there is, right? Deploy, duplicate, sorry. Health reporting issue, okay. Must be followed. Not acting on a WOW switch fault could result in WOW switches faulting on a future flight, which can cause erratic flying qualities, making it difficult for the pilot to maintain control of the aircraft. That statement really underplays the significance of things. And like I mentioned, is that because the people involved didn't realise the severity of the outcome, or is it because and I'm not trying to point fingers here. I'm just trying to play both sides of the argument, devil's advocate. Did they play down the potential implications of it for whatever reason? I'm not accusing anybody. I'm just exploring ideas. That's what the purpose of this is: being open, honest, trying to be as humble as possible, and think about all possible scenarios without assigning any kind of blame or guilt or anything like that. So thanks for that, Andrew. I really appreciate that. Fantastic. Right, the newsletter identified HRCs relating to the main landing gear WOW sensors, several of which were present during the 28th of January mishap and reported by the mishap pilot during the conference hotel with the SOF and Lockheed Martin engineers. Interesting. So you'll remember this from yesterday. This was the conference hotel people. So I would like to assume, and I don't know this to be true because it doesn't say yet, but I would like to assume that this information was in their knowledge, so they knew about that, so that they could make decisions. Because they were told about the 5 HRCs, the health reporting codes. So were they aware of this information? I don't know. We don't know. Fantastic. Weather. Okay, weather. It was... let's have a look. Winds 4 knots, temperature -1. What did we say -1 was earlier on? I can't remember. It was cold. It's bloody cold. -17. There we go. -17. Well, it's even colder than that because it's 0 there. So -17. Sorry, -1. -5, visibility 15 miles, ceiling 4.5K, no significant weather with freezing level at the surface, temperature at flight level 10,000 was -29. Oh, that is a bit chilly. It's interesting they put F and then C there. Yeah, I don't know why that is. Okay, so we are nearly at a good point to stop. So what time is it? 1:05. Should we keep pushing to there? Yeah, let's do it. Observed weather at Ilsen Air Force Base at 21:55 Zulu was reported to be 3 knots, 10 miles. Scattered light cloud, broken at 5. Temperature -7. Oh, right. So just an observation then. So I mentioned earlier on that if the weather was different, if it was IMC conditions, this could have been a lot worse than it actually was, just because of the change in the context. Anyway, crew qualifications. The mishap pilot was a current and qualified evaluator pilot, so they're obviously shit hot at what they do. The mishap pilot had a total of 500 hours in F35, 51 of which were evaluator hours. 400 were instructor hours, so they're really highly qualified pilots. The mishap pilot received his evaluator qualification on 19th September, instructor qualification on 2020, mission qualification on October 2020, initial instrument qualification 2020, prior to qualifying the F35, previously a qualified instructor in the A10. Wow, that is so cool. I love the A10, it's my favorite, one of my favourite aeroplanes. An instrument qualified in the F16, wow, blooming heck. The MP had a total of 2,700 career flying hours. The mishap pilot was most recent evaluation was in August 24, where he was qualified with no discrepancies. During this evaluation, the mishap pilot received a commendable in the area of flight leadership and instructor performance. A commendable rating is awarded if the examiner's determination the aircrew members demonstrated exceptional skill and knowledge. So he couldn't have had a better pilot pretty much in the cockpit at the time. Brilliant. So these are the hours. Yeah, okay. Medical. Qualified for medical flight duties. Medically qualified. No duty limitations. Medical review. No other factors relevant to mishap. In good health. Review of the medical records did not reveal any illnesses or duty limitations. There's no evidence to indicate the MP's health was a factor in the mishap. He sustained a compression fracture of the thoracic spine and superficial abrasions to the neck and face as a result of the mishap. I hope Martin Baker get them a Breitling watch as compensation. Anyway, pathology, toxicology samples were obtained and submitted to the Armed Forces Medical Examiner System for analysis. for all relevant parties, so that includes maintainers presumably. Negative results for drug abuse or of drugs of abuse panel, ethanol, methanol, isopropanol, and acetone. Great. Lifestyle. The 72-hour and 7-day histories were obtained under safety, privilege, confidentiality, and not available to review for the purposes of this board. Based on the mishap pilot statement, initial medical response, medical record, and lifestyle information provided to flight surgeons as part of the initial medical response, there is no evidence to suggest life cycle factors were a factor in the mishap. Crew rest and crew duty time. There is nothing to suggest that the mishap pilot did not comply with published crew rest guidelines at the time of the mishap. Okay, great. So I think that's a good time to sort of have a pause there. There are other sections that we're going to go through, probably tomorrow now, maybe later on today if I get some energy back. But one of the things I want to sort of observe is that the style of this investigation report, the structure of it, is very much about the operator of the aircraft, the direct controller of the aircraft. And so in this case, as you've seen, I've got sort of two control structures preliminary at the moment. One about the operation of the aircraft, and one about the maintenance of the aircraft and the hydraulic fluid and the supply chain associated with it. Now, this investigation report, up to this point, has been very much about the pilot, as you would expect. But what about the people involved in the maintenance? What about the people involved in the management of that maintenance? Why is that stuff not discussed? And again, it's probably because this is a standard, format template for this kind of investigation. But if we're going to use CAST in the future, or STPA, we have to be thinking more broadly than that. Who else, what else is involved? How do those controllers contribute or not? And of course, in the investigation report for a CAST investigation, we would explore each of those controllers individually and understand what the context was around their control actions, their contributory control actions. So there we go. That's the end of today's session. I hope you've enjoyed it. I hope it's been interesting to you. Of course, if you've got any questions or comments about this case study, you're welcome to come along to the live session a week on Friday the 3rd of October. I'll include the link for registration below. It is going to be a Zoom meeting, so you'll be able to interact with me directly. If you have any questions, I can bring you up on screen and talk about it. And I'm hoping we're going to have some really engaged people that can provide a lot of technical or expertise feedback that I can't provide. So it should be a good session. And of course, if you need some help with CAST or STPA, or you just want to have a conversation about it to see how it could benefit the things that you do, please send me a message. We'll set up a call and we'll see how we can possibly help. So yeah, thank you very much for watching, and I'll see you on the next video. Take care.